Okay, so as we go back to chapter 27.1, talking about electric current yet again. And we mentioned something last time that in order to have electric current, we have to have a difference in potential in order to have a net electric field to go through this particular wire. And let's say that we have, for charges to flow, so we have a wire with a particular cross section within it. And if we had connected this wire up to the same potential, like this one wire and a battery that's connected to both ends are connected to the positive terminal, well, then the charges within, this, wire would not even flow because it's the same potential. We don't have a net electric field through which an electric force could move these charges and have work done on it and all that good stuff, kinetic energy or current, as we're about to discuss. So there's something called electric potential energy, which is basically just voltage, a potential difference, which is the final minus initial points. If this was B and this was A, so there'd be a potential difference between these two terminals. And we also know that voltage difference is proportional to an electric field. Well, we can't have an electric field if we don't have a voltage difference. If delta V equals 0 and this is 0, then it doesn't matter what kind of distances the charges could flow through. So that's why we need a net electric field. So in this situation, the electric field, the net electric field basically is 0. So in order for charges to flow, we have to have an electric field which is set up through a potential difference between these two terminals, which would be positive and negative, A, B, and then we'd have a wire of a particular cross section. We have charges, let's say these would be positive charges that are going to be moving under or within an electric field, within the medium of an electric field. So let's say our electric field will be going from left to right, because we know conventionally that electric fields start from positive sources and end on negative. That's going all the way back to chapter 23. So these charges are going to be flowing from the positive terminal through, let's say, this cross section here, all the way through. Well, basically these charges are going to be flowing through this wire. And so the positive charge is going to the negative terminal, and the negative charges doing vice versa, going from the negative terminal all the way up to the positive terminal. So this definition of current is basically the rate of change of charge flow through and we get a rate of change of charges flowing if we look at a particular cross section in this wire, and then we say, okay, the difference in charges on the left and right flowing in a certain amount of time through this cross sectional area, we define as current. So current is basically, or average current is basically the rate of change of charge flow through this cross sectional area, or delta Q over delta T, and we can also just call it dq dt if you just want to write it in the calculus equivalent, dq dt. So that's all current is. It's a rate of change of charge flow. What are we what's our parameter? What's our ground for making this a rate of change? Well, which is talking about these charges that's flowing through this cross-sectional area that's right here in the middle, cross-sectional area A. So that's our basis for saying rate of change. What are we changing through or within? Well, we're having a rate of change through this area, and so current would just be the rate of change of charge flow, or delta Q over delta T. Through any section of wire. So this is just our arbitrary cross section. So our SI unit of current is the ampere. We call the amp, and 1 amp is equal to 1 coulomb per second. The direction of current is going to be from positive to negative. That's our conventional current. We know we can have electrons flowing from negative to positive, but conventionally, in terms of the electric field, we're going to look at current in the same direction as the electric field direction, the conventional electric field direction. So our direction of conventional current is flow of positive charges. So when we're going to look at a circuit, we're always going to begin the current flow from the positive terminal all the way back to negative. So this is kind of like a macroscopic view of current flow. So again, let's take a look at the microscopic view. The microscopic model. So let's say that we're inside of the wire and we're going to look at each individual charge. Looking at all of the charge carriers, in number of charge carriers. And some volume of wire. Why is it a volume? Because we're looking at these charges flowing through a cross-sectional area A over a certain length. So that's going to be our volume that we're going to look at. So we can just take the same cross-sectional area as far as my picture goes. It's the same cross-sectional area for this entire picture. So we have all of these little charges flowing through this cross-sectional area. So we're going to call each charge Q, and they're going to be moving with what we call a drift velocity, V sub D, or just the velocity of the current through the velocity of the charges through the wire. They're drifting along, or they're bombarding into other charges as they go through the charge carrier. So they're not really unimpeded. So they're going to be moving forward, but there's going to be a certain lag or drift as they hit other charges. So the delta Q that we defined for current is going to be redefined in terms of the number of charge carriers in over this volume A delta X, surface or cross-sectional area A, and delta X is our displacement to make the volume, and n number of charge carriers. So I could really just write NQ A delta X. That's going to be our definition of charge difference from either side of the cross-sectional area. So we just have like a Q initial, Q final for delta Q. And on the microscopic level, it can be defined in this fashion: number of charge carriers through that volume. So again, this is the number of charge carriers cross-sectional area. So displacement or length, and Q is the charge. So we also noted that in some time delta T, all the charges are going to move with some drift velocity we call or speed. once we get down to those certain terms, it really doesn't matter. It really doesn't matter. It's just trivial. Call it velocity, drift velocity. Delta x over delta t. Where the length of the wire, or the displacement, the delta x, so v d delta t. So now we can just go back to our microscopic definition of delta q and make this substitution for delta x. So NA v sub d delta t q, and then we put it into our macroscopic definition of current, and now delta q is going to be in terms of the microscopic charge carrier. So now we can take the macroscopic view and transform it into the microscopic view. So therefore, macroscopically, large view, we have that. Just, we're just collecting everything at once and letting all the charges flow in a certain amount of time. That's just going to be equal to and the delta t's cross. So we just have NA drift velocity q, and that is our current on a microscopic level, because we're looking at every individual charge as opposed to a collection. We're looking at the whole picture, with delta q over delta t and each charge carrier, the small view, microscopic view, in terms of this picture here, this formula here. Okay, so now let's go to the concept of resistance. So we have charges flowing through this wire, through cross section, and we're just going along in the presence of a net electric field. But all resistance is how much are your charges going to get impeded by other charges? How much do other charges resist the flow of your current or the material? So resistance is just, the rate at which your charges are not going to move as well. They're going to be resisted. And depending on the material and the collisions that charges will experience will be either high or low. Just depends on how many collisions they make with other charges. And we define the resistance in a circuit is usually characterized by a circuit element called a resistor. So, because it's in a resistor that the charges experience the most amount of collisions in the circuit. So the less amount of collisions, the least amount of resistance, more collisions, more resistance in that circuit. And if you have resistors in series and in parallel, you're going to get different degrees of resistance in those cases. So we start off by defining something called current density. And that's just current per area. And the reason why we say current per area is because all of these charge carriers are going to be flowing through cross-sectional areas. And it's very similar to surface charge density, which is charge over area. And this is current density, which is current per area. similar makeup there. From our microscopic view, we can take a look at current that we just arrived. Put that expression here. And the A's cancel out. And then we have a microscopic view of current density, which is in VDQ. If we knew the number of charge carriers and what each charge is basically, and the drift velocity, we can find out the current density. Or if we just knew the whole current as a macroscopic viewpoint, we just knew, the rate of change of all those charges flowing, we could use this I over A. So what is the current in amps divided by the cross-sectional area? We get the current density. Well, current density is proportional to electric field and empirically defined with this equation. Now this sigma, not to be confused with this sigma. This is, we'll define this as the conductivity of the material. How much, depending on the type of material that it's made out of, that material would be more conductive than another material, like copper wire versus aluminum, magnesium, or steel, or iron. They all have conductivity in indices here.
Oh, it's a constant, you mean?
It is a constant. Depending on the material, it's going to have its own conductivity rate.
Okay.
Yeah. So let's just go ahead and put that here. Conductivity of material. It's all context. So we'll know in context that this sigma does not mean this surface charge density. The problems will meet out the context. And E is electric field. So that should make some sense on an intuitive level, hopefully, that in order for charges to flow, you have to have an electric field, which is the medium for an electric force to go from one potential to another type of potential, or from a high potential to a low potential. We do that via an electric field. And the density of this current is going to be given as the conductivity of the material multiplied by the electric field through which these charges flow. So that is our empirical understanding or viewpoint of current density given by this formula. So conductivity, or materials that are conductive, are said to obey what is called Ohm's law. And we'll get to Ohm's law here in a moment. Materials obeying this are said to follow Ohm's law. And all Ohm's law is a relationship between the voltage and the current in a circuit. So we'll take a look at that. So now that we have all those definitions here, let's take another look at a segment straight wire cross-sectional area A and length L. So we have a volume again. Through this wire from point to point, we have a potential difference or a voltage difference, potential difference, all semantically the same. V final minus V initial, VB minus VA. So that's going to go through the wire. Remember, voltage, you cannot have a voltage if you don't have a net electric field. And you get a net electric field when you have a difference in potential. They're all related to each other. They all depend on each other. As we started at the beginning, if you have two potentials that are the same, no net electric field, no charge flow. Must be a difference in potential, a voltage difference that will set up an electric field from conventionally from positive to negative. And so yeah, so we have this voltage difference that goes through this wire. Again, the picture, cross section for the charges, at least that's the viewpoint, positive, negative, a voltage difference. So we have an electric field from positive to negatives. And so that is the relationship. Delta V proportional to E. Right? We don't have that, we, don't have a voltage difference, we don't have an electric field, charges are static. So now, going back to the and equation for voltage, delta V equals E times D, or in this case, L. L is our distance. We know that current density in terms of electric field is given as sigma times E. Remember, this is conductivity. Therefore, E, we solve for E, will be delta V over L. And we substitute in here. And we also know that this is equal to I over A. So if you will, well, there's both macroscopic views, which is just two different ways of saying the same thing. Sigma delta V over L equals I over A. Empirical definition of current density. Because I over A is J, current density. Delta V, which we're going to look at up here. Delta V is equal to JL over sigma. And again, we get this relationship by manipulating this guy. So I'll solve for delta V. Hope you guys can see that. So L divided by sigma. And that becomes, and we know that J is equal to I over A. So this becomes I times L over A times sigma. Now, I is itself, I is a current. Well, it turns out that these constant terms, so for whatever wire it is, let's say it's copper, high conductive index, than say aluminum or whatever. It's copper wire. And let's say that copper wire has a particular length, a particular cross-sectional area, and a particular conductivity. So this whole thing is a constant that we denote as the resistivity, or basically just the resistance of that wire. Length over the particular wire's length divided by its area, cross-sectional area, and its conductivity index denotes the resistance intrinsic in that particular wire. So copper will be different than aluminum, than steel, than nickel, or whatever the material is. Because this constant, even though this may be a constant for copper, whatever the conductivity is and the area and the length is going to change for different materials. So this expression here is known as the resistance in the wire. Resistance is measured in ohms, after George Simon Ohm, symbol omega. Another way we can look at resistance is a relationship of voltage over the current. The units, ohms here, will be the same as what we get here. So this would be, say, meters over meters squared. And I have to look in my book for the conductivity units, but they all come out to be ohms. This is taking a look at resistance in terms of, say, let's say that we had a circuit with material that was basically, they had no resistance in the material. So like we were connecting a battery, positive terminal of battery through a wire to the negative terminal. So that's basically negligible resistance. It's been measured that, right, through experiment. Now, if we crank up the voltage in that particular circuit, the current will go up at the same rate. So there's like a delta V versus I graph that we can get here, where both of these are directly related, directly proportional to each other. So when we take the slope in between them, so as delta V increases, I increases at the same rate. So the slope in between them will give us the resistance in that particular wire or particular device in the circuit. So this slope here will be our resistance. So this relationship here, in terms of voltage and current, gives us the same relationship as this viewpoint when we take a look at current density. So L over A sigma is the same as this ratio here. So resistance. Resistance, again, is just how much are your charges getting, try not to use the word resistance, but how much your charges being resisted as they flow through the circuit. All right. Kind of impeded. How many collisions on a microscopic level are your charges experiencing? So that's the microscopic viewpoint of resistance. If there's a large amount of collisions through a particular device, then you're going to have a large resistance. So from that last equation for resistance, delta V over I, resistance is measured in ohms. 1 ohm is 1 volt per amp, because delta V is measured in volts, current measured in amps. So we're talking about conductivity here, right there. So this 1 over sigma business is going to be the inverse of conductivity, which we're going to call resistivity. The inverse of this regular sigma, sigma times E, is the resistivity. So 1 over sigma is resistivity, whereas sigma, conductivity. All right, and we define resistivity as a variable rho, 1 over sigma. And since we define R to be this constant here, L over A naught, A sigma, then resistance can be written in another way, which is rho times L over A. Remember, 1 over sigma is rho times L over A. Resistance is the resistivity of the wire times the length of the wire divided by the area, the cross-sectional area of the wire. This will give you the same value if you knew the voltage and the current, and give you the same value, if you didn't know resistivity, just L over A sigma. So there's 3 different ways of defining resistance. Add it up here. So now you take a conductive piece of material, charges are flowing. If you heat up that material, you're going to increase your resistance. Hey there, you're going to increase your resistance. And we have two formulas that relate. Okay, increase your resistance and your resistivity. So we have two formulas for resistivity and resistance. Their dependence is on temperature. And there's a linear dependence for both. So as you increase temperature, your resistivity goes up. You increase temperature, your resistance goes up. And resistivity is just it's a property of the wire. The resistance is the overall, ability for charges to be impeded, which is a function of the resistivity. But we're going to separate both resistivity and resistance here. Resistance and temperature. So the resistivity varies linearly with temperature. Okay, and that looks like this here. Rho naught, that's the initial resistance. This is the intrinsic resistivity of the wire before you heat it up, rho naught. You heat it up, now rho naught becomes rho. 1 plus alpha T minus T naught. Now you get this formula through experimentation. We're just going to take it on face value for now and proceed on. Alpha is the coefficient of resistivity, and it has its own expression. So let me just do this here. This resistivity after heating, changing it from T naught to T. Original resistivity, and alpha is like a proportionality constant between the new resistivity and temperature difference, basically. But it's inversely proportional to the temperature difference. So yeah, let me just write that expression for alpha: 1 over rho naught delta rho over delta T. And we can kind of see that from the formula if we were to, solve for alpha. Yeah, this would, delta rho, well, divided by rho naught. And this is rho naught here. So yeah, we can, once we take this guy around and solve it out for alpha, we can get this relationship here. Again, I'm gonna leave out some of the trivial details for the moment for I'm gonna get ahead, but you guys are great at math. You can do that. Now resistance R naught 1 plus alpha T minus T naught, basically the same thing. Resistance as a function of temperature. So we now have like 4 formulas for resistance as a function of temperature, as a function of length, resistivity, and voltage and current. So it just depends on what you have. I can find resistance in a number of ways. So the more ways we can find something, the better. It just helps out. So you can, expand our understanding of things. So yeah, this here coefficient of resistivity, and conversely, in context, the coefficient of resistance. Be kind of like the same thing, 1 over R naught delta R over delta T. Questions so far? Basic definitions. If you want something to be super conductive, reduce your temperature to almost zero, and there will be basically no resistance in that wire. So it becomes a superconductor. Okay, superconductivity. You know, huge part of material science, and I may be misspeaking, but solid state physics uses, you know, does a lot of experiments where, a lot of experiments in superconductivity. But the basic concept of superconductors is that if you have a material, read my own writing, that's cooled. Material's cooled below a certain temperature. We'll call it a critical temperature, TC. I'm reminded of statistical mechanics when I see that. Called the critical temperature. By the way, one of our final projects in my graduate school class for statistical mechanics was to give a presentation on what we call the Ising model. Basically, the microscopic viewpoint of magnetism under certain conditions. There were different conditions through which particular type of magnetism could you could measure, or you could basically measure, but basically the word I'm looking for. You could test, you know, different conditions. But yeah, bit of a tangent. And we use something called it's critical temperature was in that particular experiment was a key point to go from different types of magnetism. But all right, I'm going off on a tangent. So anyway, superconductors. Materials cool below a certain temperature TC, I call it critical temperature. You know, for superconductors to be superconductors, you know, the temperature gets very small, almost zero, or small. Small enough, the resistance goes to basically nothing. So yeah, if you can get your temperature to almost absolute zero or close to it, you're in the realm of superconductivity. Okay, 27.6, the electrical power. Circuit, going around, a resistor, positive terminal, high potential, low, R, charge coming in, conventional current flow, right? From positive all the way to negative. That's our direction of conventional current, which we'll see even more. Okay, so as each charge goes through this resistor, it's going to, the energy that it has from its battery, it's going to be losing the energy that it has from this battery. Some of the energy is going to be lost to this resistor through the collision. And that energy is going to be gained by this resistor. So the energy loss from the charge, right, is going to be the energy gain by resistor. So we have a conservation of energy here, yet again in a different form. So our resistor symbol. That it takes a certain amount of time for energy to be lost. So we basically say, and let me not forget that delta U is Q delta V from earlier definitions. The rate of change of energy loss is power. delta U over delta T. Let's see, algebraic form, calculus form, rate of change of Q delta V. Well, we know we have our dq dt delta V, basic definition of current, so I delta V. One equation for power. We also know by the way, I forgot to write this earlier, but this is Ohm's law in a nutshell, delta V equals IR, because we were looking at a resistance in terms of the relationship of voltage and current. So if I solve for delta V, it's going to be I times R. And without the semantics of R equals delta V over I as Ohm's law versus delta V equals I times R as Ohm's law, I'm going to categorize everything here as Ohm's law, because Ohm was the one to find the relationship of voltage and current to be resistance. And depending on the materials, you're going to have a different amount of resistance from material to material, right? And it's basically summarized in this formula here. So anyway, delta V, I times R. From that, we can substitute voltage into this equation. And let me go over here. Squeeze it down too much here. So we can say P equals I V, I times R, and that just becomes I squared R. It's another equation for power when you know current and resistance, current and voltage. Also too, from Ohm's law, current is voltage over resistance. So we can substitute this expression into the I squared R, and then we'll have V over R squared times R, E squared over R squared times R, and our last equation for power, E squared over R. Power is measured in watts. Okay, energy per time, joule per second. And so yeah, P is V squared over R, I delta V, I squared R. Let me summarize. There we have it. That's basically 27 again. Any questions? Kind of review, should be reviewed. All right. Let me pause here. Okay. So I figure, instead of writing everything again, we've seen this. So I would just go back to what we saw before. Chapter 28, 20.2, you have resistors in series and parallel. When you have resistors in series, they're just one after another. So resistor 1 followed by resistor 2, resistor 3 will be, and so on and so forth until we get from start all the way to finish. The current for both of these resistors will be the same. Not going to derive that here, just we're going to take that for our efforts going forward. But the current for both resistors will be the same, is the same. The voltage drop across each resistor is different, because if we were taking a look at this positive terminal and going to say the end of the resistor 1, that would be one particular potential difference, because we know that potential difference of voltage is the difference between the difference in the electric potential energy between 2 points, and the voltage difference, the potential difference between 2 points. So from the positive terminal of this battery to the end of R1, is going to be different from the positive terminal to the end of R2. That's why the voltage drops are different. Now, if we're just talking about the entire battery, obviously, we're going from start all the way to finish. So that's going to be, say, 9 volts, whereas this could be 3, this could be 6, to make the entire 9. So the voltages are different from for R1 and R2. Resistors in series can be added to make what is known as an equivalent resistor, which basically means that there's one resistor that can do the job of both of these. So equivalently, so that's why this is called an equivalent resistor. If this was 3 and 6, then we can have a resistor of 9 to do the job of both. When you have resistors in parallel, we have different pathways for current to flow. So the current will be different, but the voltage drop across R1 and R2 will be the same because they occupy the same distance between A and B. They're both in between A and B. So the voltage drop for R1 and R2 will be the same, whereas the currents will be different. So it's just a, vice versa or inverse relationship between series resistors and parallel resistors. So in the equation, it's reflected in the equation, the inverse addition between series resistors and parallel resistors. So for parallel resistors, we have 1 over R equivalent equals 1 over R1 plus 1 over R2. And if we were going to simplify this in terms of R equivalent, because even if we did this, we would be getting the value for 1 over the equivalent. So we'd have to flip it over, do the inverse to get the equivalent resistor, because we don't want 1 over R equivalent, we want the equivalent resistance. So if we were going to simplify that, common denominator would have this, and we multiply R2 over here, R1, and then that would be 1 over R. But then R would just be the inverse. Just flip it over, reciprocal, that is, just R1 times R2 over R2 plus R1. And that would be the equivalent resistance for 2 resistors in parallel, just using this formula. This and this, the same. So depends on what resistors you have. Usually the problems will have the resistances where you can find an easy common denominator and your life's easy. So series resistors, you add them. Parallel resistors, it's the inverse of this, 1 over R1 plus 1 over R2. It's the fractional equivalent. So yeah, again, wrote here that the currents are not the same for parallel resistors. Voltages are the same. And yeah, so that's basically all it for 28.2. And then we did a sample problem, I think. Maybe we can do another one before we get into Kirchhoff's, because now what I want to do with Kirchhoff is write this up a different way and hopefully make it easier. Let's go to 27.2. So you're now on page, let's see, 800 and page 800. We're going to do question 5. I'll pause this. So we have the setup circuit with 4 ohms. We have 7 and 10 in parallel, and that's going to be in series with this 9. So we don't have a battery yet. And then part A, we're just to find the equivalent resistance of the circuit. So kind of a rule of thumb is like, anytime you see the parallels, break those down into just one equivalent resistor so that you can add these guys up in series. So wherever you see the parallels, break those down into one, and so then you can just add. So that's what I did here. For resistors in parallel, 1/7 plus 1/10. Common denominator, you got 10/70 plus 7/70, you get 17/70. But that's 1/R. You want R, so we flip it over. 70/17 equals 4.11 ohms. And then you just add them together. So basically what that says here, the 4.11 ohm resistor will do the same as 7 and 10 in parallel. 4 plus 4, 11, plus 9 is 17.11. Now we have a voltage of 34 volts. We can use Ohm's law, of course, to get the current through all of the resistors. Now for the entire circuit, so we can start there first. Rule of thumb is we can start with what is the current in the entire circuit? Well, if we had one big resistor of 17.11 ohms, we can find it. So 34/17.11, 1.98 amps. That's the entire circuit. If you will, you can say the equivalent current or the total current and the total voltage and the equivalent resistance, all these EQs to get the entire circuit throughout the current throughout the entire circuit. Now, from this configuration, you can break this down and you know that the 4 and the 9 are going to be in series with each other. So this current that goes through the entire circuit is going to be the same current throughout all of these resistors. So I said here I4 and I9 because I'm going to do something special with the 4.11. But even in this configuration, at least right now, the current through the 411 ohm resistor, the 4 and the 9 are going to be the same. We don't want the current through 4.11. We want the current through the 7 and the 10. So we got our I4 and I9 already. You following that so far? Because 4 and 9 are going to be in series with each other. Here's 4, here's 9, they're already in series. The trick is dealing with the parallel ones. We know something special about parallel resistors. We know that the voltage will be the same across both and the currents will be different. But whatever the currents are, they will add up to 1.98. And that's like a implicit segue into Kirchhoff. So the current coming in is going to be the current going out. So whatever this is and whatever this is must add up to 1.98 in and out. So the voltage across the 4.11, I times R, what I'm doing here is to get the voltage across both, because I know the voltage will be the same, 8.13. And so the current across the 7 ohm resistor would just be voltage over resistance, 8.13 divided by 7, 1.16 amps, roughly. And figs and stuff. So the current across 10 ohm resistor will be 0.813. Add them together, be 1.98. They're pretty close to it. It's just a sig fig off or whatever, but it's basically, yeah, 1.98. Did you guys get those?
Yeah.
Great. So that's how we deal with the introduction here. Into and dealing with parallel and series resistors. Jeremy, did you get that?
I get the basic idea. Yeah. Like parallel and series, like how you add them.
All right, so let's go to 28.3 again, Kirchhoff's rules. And so give you a complex circuit here. So really Kirchhoff's rules work for very complex circuits. You know, you have multiple loops, multiple batteries, and you're trying to find currents in all of these resistors, voltage drops, resistor values. So it's not just one battery, maybe a couple of series and resistors in series and parallel. You have multiple arrangements. You can have 2 and 3 batteries in the same circuit. And so we're going to have to deal with that in a special way. So there are two rules in Kirchhoff's rules. There is the junction rule and there is the loop rule. The junction rule deals with currents. The loop rule deals with voltages. So let's say that we have a particular junction like we had in our previous problem. And for the junction rule, the statement is that the sum of the changes of all currents must be equal to 0. So that means basically whatever the current coming in is going to be the same as going out. So let's say that this is current 1, let's call it I1 because these are going to be two different legs. Call this I2 and I3, and this will be I1. So the sum of all the currents equals 0. It's conservation of charge. You're not going to have any charge buildup. You're going to get the same amount of charges coming in as going out. Everything's conserved, all that stuff. So our job is to figure out what currents make up 0. What's going to satisfy this condition? You can leave now. Let's see.